Good morning, friends. Hope that you must be good. Today, I'll be discussing with you the development of Navier-Stokes equation. What is Navier-Stokes equation and how to derive it? So, let us start. Before development of this particular equation, let us try to understand the system of stresses in a deformable body. So, consider an element like this. Now, this particular element is not of a control volume, but this is of a control mass system. So assume that we have taken an infinitesimal element of a control mass system. Now, before starting anything, consider the coordinate with respect to which we will be analyzing the problem. So this is our coordinate, that is x, y and z axis. We will be deriving this particular equation in Cartesian coordinates. So to start with, what you should always remember that the stress on the positive phase in the positive direction is positive, and also the stress in the negative phase in the negative direction is also positive. So what you can do is, for this particular element, you have this x phase, positive x phase, this one. Let me name it A, B, C, D, E, F, G. So here positive x phase is A, B, C and D. So stresses in this positive phase acting in positive direction will be positive. So this is, let us say, the direct stress sigma on the x phase in the x direction. Okay. Likewise, on the x phase in the positive y direction will be positive shear stress. So this will be tau x phase y direction. Likewise, this will be tau on the x phase in z direction. Likewise, in the negative x phase, we can do the same thing. Let me change the pen. Okay. So this is normal stress on the negative phase in the negative direction. So that will again be positive sigma x x. Okay. Likewise, this on the y phase, on the negative x phase in the negative y direction. And sorry, z direction and negative y direction. So these all will be positive. Likewise in y phase and the z phase. So to understand what is happening here, let us start with considering the dimension in the x direction dx, in the y direction it is dy, and in the z direction dz. So dx, dy and dz are the length of this element in the x, y and z direction. Okay, so now you have understood that how to write stresses in a particular phase. Okay, now let us start with the derivation. So what I will be doing is, I will be solving for x direction, and in the y and z direction similar trend will be there. So the equation will be very much similar. Okay, so first draw the element again. So this is the element. Okay. Okay. So this is the element. Okay. Now let us say that the stress is sigma xx. Okay, will be the stress on the negative phase in the negative direction. So after a distance dx, with the help of Taylor series expansion, you will be getting sigma xx plus del sigma xx by del x dx. Now this will be the stress in the x direction on this right face after a distance dx. Now we are only talking of x direction stresses, okay, and ultimately the forces. So this is the one. Now on the y face, let us talk. So this is x direction, this is your z direction, and this was your y direction, okay. So on the negative y phase, if you look, then on the negative y phase in the negative x direction will be your positive stress, okay. So as the coordinate starting from here, so on the negative phase, so this will be the negative phase, the front face will be the negative phase. So in the negative x direction, so this is the one and this is the negative x direction, so this will be tau on the y face in the x direction. So this is the one. What about on the positive y? So positive y, this is the positive y face behind one. So in the positive x direction, this will be after a distance of ty from the Taylor series, it will be tau yx plus del tau yx by del y dy. Okay. Now we will be talking of the stresses in the x direction on z phase now. So this is the negative z phase. So on the negative z phase in the negative x direction will be the positive stress. So, mm, so this will be tau on the z phase in the x direction, and after you move to a distance of dz, this will be tau zx plus del tau zx by del z dz. So now you have written all the stresses on all the faces in the x direction, either in the positive towards the positive x side or towards the negative x side. Now what we will be doing is we will be converting this into the forces. So let us start with the x faces. So x faces, if you look, this is uh, sigma xx, okay, acting in the negative direction, okay, this, and the area on which this is acting will be equal to dy times dz, dy times dz, and this one also, that is plus sigma xx plus del sigma xx by del x dx on what plane? Again x plane, that is dy dz. Remember one thing, some people used to call plane, basically a plane is represented by the axis itself. A plane qualifies to be called as x plane if the plane is normal to the x-axis. Likewise, a plane qualifies as the y plane if the plane is normal to the y-axis, and for z as well in a similar way. So this is the x direction forces on the x face. Now let us try to write the y x direction forces on the y face. Now you can see this is the first one, that is tau y x, and this is in negative direction. The plane is y, that is dx dz, okay. Then this is the one, so this is plus tau yx plus del tau yx by del y, this is dy times dx dz. Likewise for the forces in the x direction acting on z faces. So So first is this. Okay, so it is tau zx negative direction and acting on z, that is dx dy plus this force. Okay, so it is tau zx plus del tau zx by del z dz acting on dx dy. So if you look carefully, what is happening here, this dx dy dz and dx dy dz will cancel out, likewise these and these. So the net force in the x direction will be equal to sum of all these, that is del sigma xx by del x dx dy dz plus del tau yx by del y dx dy dz plus del tau zx by del z dx dy dz. And what is dx dy dz? Dx dy dz is the volume of this particular um, small infinitesimal system. So what I can write is plus tau yx by del y plus tau zx by del z times dx dy dz, which is nothing but volume of this element. So this is the net force acting on this fluid volume, that means fluid mass system infinitesimal in the x direction. So let me write this as net force. What people used to say, they always talk in terms of specific quantities, that is, they always talk per unit volume here. So what I'll write, Fx will be equal to the force in the x direction per unit volume. So that will be equal to you, this volume will come onto this side and it become per unit volume. So it is simply del sigma xx by del x del tau yx by del y plus del tau zx by del z. So this is the total force acting in the x direction per unit volume. Likewise, we can also go for y and z. So if you solve this further, then you will be able to get this particular equation for the y direction. Tau z y, and in the z direction likewise. It is tau xz plus del by del y tau yz plus del by del z sigma zz. Okay, I hope this thing is clear to you. And one thing you should always remember, that stress is a tensor quantity, that is, it requires two directions to be specified correctly. And you can very well appreciate the fact that this is having in totality 9 components. Okay, and in this particular matrix, the columns represents the planes, that is here you can see this is the x plane, this is for the y plane, and this is for the z plane, and the row of this particular matrix represents the stresses in a particular direction. For example, this is x direction, this is y direction, and this is z direction. So column represents the planes and the x direction, and the rows represents the x direction. And one more thing which you should understand here is that, and you might have also gone through this in your strength of material forces, that this is a symmetric tensor. That means the tau I, this term and this stress will be always equal. So in totality, how many unknowns? Previously you said that 9 components will be there. Okay, no problem. But out of these, only 6 will be independent. That means 6 you have to calculate, because tau xy is same as tau yx, tau zx is same as tau xz, tau yz is same as tau zy. Okay, so this should be very much clear to you. So now we have the forces acting on the system, infinitesimal system, that is control mass system. Okay, so now the question is how to proceed further. Is this the only force? No, this is only the surface force. Basically, you, as I have already explained to you in previous classes, that the total force is the sum of body forces plus the surface forces. In surface forces you have stresses, so on acting on the surfaces, and body force means the force which is acting on the body throughout its mass. For example, your gravity, electromagnetic forces, and that all. So let us write that the body force vector, this is vector, is let us say in the x direction it is fbx. Okay, in the y direction it is fby, and in the z direction it is fbz. So this is what the body force vector per unit volume. Remember, uh, sorry, per unit mass. So this is body force vector per unit mass. This is force per unit mass. Okay. Now, as in previous case we have done for per unit volume case, so you divide this whole equation by volume. Okay. So if you sorry, if this is per unit mass, so if you multiply this whole equation by density, then this becomes per unit volume. So the body force vector, oh, sorry, so the body force vector per unit volume will be rho times fbxi, rho times fbyj, and rho times, I'm sorry, fbzk. So this will be body force. So in totality, so the total force acting on this element in totality, you know, the net force acting on the element per unit mass, uh, or in fact total force, let us write. So the total force acting will be equal to mass of the system times the acceleration. And acceleration here will be nothing but total acceleration. So if this is the velocity vector, then this is the total acceleration, that is substantive or material derivative of the velocity. Okay, because we are talking of what? System. Okay, so what is v here? V is the velocity, that is ui plus vj plus wk, where u, v and w are the components of this velocity in the x, y and z direction. Now the force can be written, total force can be written as uh, body force plus surface force in x direction, y direction, z direction, likewise accelerations. Okay, so what is the normal convention is we used to write this term, that is the mass times acceleration term onto left side. So if I want to write this as total force per unit volume, then divided by volume, so mass divided volume will be density. So rho dv vector by dt. Remember, this is a vector quantity. Okay, so the total force in the x direction, the total force in the x direction will be rho du by dt. In the y direction will be rho dv by dt, and in the z direction will be rho dw by dt. So this is the total force in x, y and z direction, that is the acceleration in that particular direction times the density. So let us solve, let us try to understand this. So left side we will be writing this acceleration term first. And then on the right side, there's total force. So body force plus surface force. So body force, it is rho FBX, and the surface force which you have already developed here, this. So this will be del by del x sigma xx plus del by del y tau yx plus del by del z tau zx. So this is the equation or the momentum equation or the force equation in the x direction. Likewise in the y direction, first the body force and then the surface forces plus del by del y sigma yy plus del by del z tau zy. Likewise in the z direction will be rho fbz del by del x tau xz del by del y tau yz and del by del z sigma z z. So this becomes the force equation in the x, y and z direction. Okay, I hope till this point it is clear to you how to relate the velocities with the stresses. So this equation is your uh, momentum equation or the Newton's second law in terms of stresses. But friends, what is important that we should know everything in terms of velocity. And one thing which usually people get confused that this equation is for incompressible flow because density is outside. No, remember, density is coming out not because the fluid is incompressible, but we are talking of a controlled mass system. The element which I have drawn is the system itself. That means the element having fixed identity. Okay, so that's why this row is outside, not because that the um, uh, fluid is incompressible. No, this is not the case. Now the thing is, there should be, now from where we will be getting velocities. So the velocities will come from the relation between stresses and strain. So how to get those relations? So to get those relations in a correct fashion, um, you should assume something. So what are the basic assumptions? So in the relation, the assumptions are, first, the relation between stress and strain is linear relation between stress and strain. Second assumption, the relationship is invariant with coordinate transformation. That means we are talking of a physical law. That means whether it is rotation or translation, the relation remains the same. So this relationship is independent of coordinate transformation. This is a very important assumption. Third assumption is that the fluid, whatsoever it is, it should obey the Stokes law. That is, the fluid should follow the Stokes law. This is a very important assumption. And by this, it means the second coefficient of viscosity should be 0. Okay, so any fluid for which the second coefficient of viscosity is 0, That particular fluid is called a Stokesian fluid. And what does this particular thing mean? This particular thing means that the viscosity which arises due to the exchange of energy or momentum between different degrees of freedom, like translation, rotation, or rotation, vibration, and so on. This should be absent. If this is the thing, then we will be calling that type of fluid as a Stokesian fluid. And the fourth and final assumption is that the continuity to hydrostatic condition. That means if you make all velocity components zero, then the equation which you will be getting should be the equation of hydrostatics. So it is continuity to the hydrostatics. Okay, so the continuity to the hydrostatics is a must. Okay, now with these assumptions, we can write what? Take here. The stresses, that is, let us take only one, sigma xx. This will be a function of what? This will be the function of direct stresses and direct strains. That means in x direction, in y direction, in z direction, as well as the rate of shear strain, matlab rate of angular deformations, and that is gamma dot xy, gamma dot yz, gamma dot zx. So this one stress is related to 1, 2, 3, 4, 5, 6. 6 strains. And how many stresses are there? Sigma yy, sigma zz, tau xy, tau yz, and tau zx. So in totality, you have 1, 2, 3, 4, 5, 6. 6 stresses, and these are related, these are function of 6 strains. So if you just talk of this simple sigma xx, then this sigma xx with respect to the first assumption, that is linear relationship, I can write this thing as E naught plus A1 epsilon dot xx plus A2 epsilon dot yy plus A3 epsilon dot zz plus A4 gamma dot xy plus A5 gamma dot yz plus A6 gamma dot zx. So total how many unknowns are there? 1, 2, 3, 4, 5, 6, 7. So 7 unknowns for sigma xx. How many stresses? 1, 2, 3, 4, 5, 6. So 6, you have 6 equation, and in every equation you have 7 unknowns. So how many unknowns are there in totality? 42 unknowns. Right? Okay. So this particular set is of 42 unknowns. And the beauty of these above assumptions is that with these assumptions which you have taken, these 42 unknowns will get reduced to only 2, that is pressure and viscosity. So the final outcome I am writing for you people, and it is, if you solve this further, you will be getting sigma xx as minus p plus 2 mu del u by del x minus 2 by 3 mu gradient of velocity vector. Similarly, sigma yy will be minus p plus 2 mu del v by del x minus 2 by 3 mu v vector, and sigma zz is minus p plus 2 mu del w, I'm sorry, there is a mistake, it is del y, del z minus 2 by 3 mu. Yes. So you can see that in all the constants have gone, and what we have got is p and mu. And the thing which is of importance here is, if you look these are what? These are the terms which make the stress equation deviate from hydrostatic condition. That's why these extra terms are sometimes also called as deviatoric stresses. Okay, now the thing is, if you add these equations up, that is sigma x plus sigma yy plus sigma zz, then you will be getting these as equal to minus 3p, or p is equal to minus sigma xx plus sigma yy plus sigma zz by 3. And this is what? This is the hydrostatic pressure, arithmetic average. And that's why we said that if this equation can be reduced to a hydrostatic condition, then that is very good, because that is what every fundamental equation should do when it is get reduced to. So what we'll do is, now we'll be replacing the values of sigma xx, sigma yy, and sigma zz in the equation of sigma. But this is not all. We have to find out for stresses also, tau xy, tau yz, and tau zx. So this will be mu times del u by del y plus del v by del x. This will be mu times del w by del y plus del v by del z, and this will be mu times del w by del x plus del u by del w is here, so it is z. Okay, now you have your original equation, that means this equation, first one. Let us talk of this equation only, because rest will be the same. It will follow the same procedure, and the result will be somewhat similar. So we will replace the value of sigma xx, tau yx, and tau zx in this particular equation and try to understand what happens. So if you do this, then it is rho du by dt is equal to rho fbx plus del by del x sigma xx. This was the equation. Del by del y tau yx del by del z tau zx. Okay, now what we'll do is, we'll replace the value of sigma xx, tau yx, and tau zx in this particular equation. So it is rho fbx del by del x of this, that is minus p plus 2 mu del u by del x. Oh, I'm sorry, there is one more term, minus 2 by 3 mu divergence of velocity vector. Okay, and then the second term, that is del by del y of mu del, this is del. So it is del u by del y plus del v by del x. Okay, and the last term, that is del by del z mu del w by del x plus del u by del z. So slightly arrange these terms. So you will be getting minus del p by del x plus 2 mu del 2u by del x2 minus 2 by 3 mu del by del x of divergence of velocity plus mu times del 2u by del y2 plus mu times del 2v by del y del x plus mu times del 2w by del z del x plus mu del 2u by del z2. Okay, now you try to club these. How? Here is 2 mu del 2u by del x2. So what I will be writing it as mu del 2u by del x2 and plus mu del 2u by del x2. So it is rho fbx minus del p by del x. One term from here and taking mu, it is del 2u by del x2. Then you have this term del 2u by del y2 plus this term del 2u by del z2. And what is left at your dispense is mu del 2u by del x2 from this term. So you again take mu outside. It is del 2u by del x2 plus this term that is del to v by del y del x plus this term del to w by del z del x. Now 1 is left, so it is minus 2 by 3 mu del by del x divergence of velocity. Okay, I hope this thing is clear to you. Now it is fbx minus del p by del x plus mu times what is this? This is del to u. Okay, now plus mu, you do one thing, you take del by del x outside because the function is continuous of velocity, so it is immaterial whether you are differentiating priorly with respect to y or x or z or x. So this becomes del u by del x del v del y del w del z and minus 2 by 3 mu del by del x del v vector. Okay, so this is nothing but divergence of velocity. So it is fpx minus del p by del x plus mu times del to u plus mu times del by del x of divergence of velocity vector minus 2 by 3 mu del by del x of divergence of velocity vector. Okay, so this is 1 minus 2 by 3, that is 1 by 3. So this becomes rho du by dt is rho fpx minus del p by del x plus mu del to u plus 1 by 3 del by del x of divergence of velocity. Okay, so this equation is in x direction. Okay, likewise you can also get the y direction equation if you follow these steps. Minus del p by del y plus mu plus 1 by 3. Okay, and likewise in the z direction, w v vector. Okay, so these equations are called as Navier-Stokes equations. These equations are Navier-Stokes equation, and each and every individual term is having meaning. For example, the left-hand term, that means this term will tell you about the acceleration per unit volume. This term will tell you about the body forces per unit volume. This term will tell you about the pressure forces per unit volume, and this term will tell you about the friction forces or viscous forces per unit volume. And in most of the BTech courses, we always talk of viscous incompressible flow. So you know, for incompressible cases, the uh, uh, the divergence the divergence of velocity vector is 0. This is what the continuity equation says. So the Navier-Stokes get reduced simply to rho in vector form. I am writing now, collecting everything. So it is dv vectored by dt and rho fbx, fby, fbz. So this becomes body force vector minus this del px, del py, del pz adding, that means the gradient of pressure, and this mu term plus Laplacian of velocity vector. So this is the Navier-Stokes equation for uh, incompressible fluid. Okay, now this is all about the derivation part, but one should very much be clear that what is the nature of this equation. This equation is basically a non-linear or sometimes quasi-linear partial differential equation, and this is having a second order. Okay, so why this is non-linear? This equation is non-linear because of the term on the left hand side, that is because of this substantive derivative. So if I expand this derivative, so this dv vector by dt in Cartesian term, this will be del v vector by del t, that is the temporal derivative, plus the convective term, that is u del v by del x plus v del v by del y plus w del v by del z. Now this is now this is basically the non-linear part. So this is the part which makes this equation non-linear. So that's why uh, it is very difficult to solve this equation. That's why this equation is so much talked of, and this is a very fundamental equation to analyze the fluid flow. Now in the next class I will be talking of um, the special cases, that is the parallel flows, where this equation can be solved very easily, and that is done by reducing this partial differential equation into ordinary differential equation. So how that will be done is the topic of discussion for the next class. Till then, thank you very much.